Hello, viewers. In this session, we are going to discuss about the stationary points for a function of two variables, x and y. So we shall consider a function z having two variables, x and y. So two independent variables, x and y. And we want to talk about what we mean by the stationary points and how to find the stationary point, and also how to determine the nature of this point. Now, a stationary point of a function is basically where the function is not changing at an instant. The point where the rate of change of the function is 0. So in this case, to find the stationary point for a function having two variables, we find the first order partial derivatives. And because the stationary point is where the rate of change of the function is 0, then we equate the two partial derivatives to 0 and solve the resulting equations. So this will give us the point where the function is stationary, or what we may refer to as the turning points if it was a function of one variable. But we shall use the term stationary point for functions having more than one variable. So in this case, because z is a function that depends on two independent variables, x and y, then the two partial derivatives are the partial derivative of z with respect to x and the partial derivative of z with respect to y. So we find these two, equate them to 0, and then solve the resulting equations. So let's talk about the types. Now, for such a function, there are three types of stationary point. The first one is the local, what we call the local maximum. So we say a point P having the coordinates x, y is a local maxima of the function z is equals to f of x, y if the value of z at point P is greater than the value of z at any other point in the immediate neighborhood of the point P. In economic terms, for example, this may represent a peak or a high point in a business cycle, indicating the maximum profit or maximum level of output within a certain context. For example, it could represent the highest level of consumer satisfaction or the peak of the firm's profit. And diagrammatically, this is how the maximum point look like. A point here where z attains the maximum. If you place something here, it will fall off. This is the maximum point of the function. We also have what we call a local minimum. A local minimum is just the opposite of the local maximum. What we call the local minima is just the opposite. So a point P having the coordinate x, y is said to be a local minima of the function z is equals to f of x, y if the value of z at point P is less than the value of z at any other point in the immediate neighborhood of that point P. So if we think of this in terms of economics, this may represent the lowest point in a business cycle. For example, it could represent the lowest possible cost of production for a firm or the minimum level of unemployment in a given economy. And this is how a minimum point may look like. Imagine that if you place a ball somewhere here, it will fall to move down to the lowest point here. This lowest point is what we are calling the local minima or the local minimum of that function. The third point is what we call a saddle point. A saddle point of a function is a point that will look as a maximum when viewed from one direction, but when viewed from a different direction, it will look like a minimum point. So this is how a saddle point may look like. Imagine this diagram, and you start from a point here, you move down. By the time you reach this point here, you'll feel like you're passing through the lowest point. Then you climb up. So when you follow this path here, because you're moving something like this, you'll feel like you're moving through the lowest point. But imagine somebody else moving along this direction. This person will be climbing up to this point here and then descends on the other side. So this person will be moving like this. So the person will feel that they are passing through the maximum point. A point that behaves this way, we call it the saddle point. In economics terms, a saddle point may signify a critical transition or equilibrium between two states. For example, in the context of environmental economics, a saddle point would represent a trade-off between economic growth and environmental conservation. Remember that policies aimed at promoting economic development, such as industrial expansion or infrastructure projects, may contribute to environmental degradation. For example, pollution or habitat destruction, leading to a saddle point where the benefit of growth may be weighed against the cost of environmental damage. Such a point is what we are calling a saddle point. And now we want to look at how to find the stationary point once you have a function. We have said the stationary point is the point where the rate of change of the function is 0. So the function is not changing at that point. So to find the stationary point, therefore, we find the partial derivatives. That's the first step. Then equate the two partial derivatives to 0 and solve the resulting equations. Let's consider this function, for example. If we have the function z is equals to 4x cubed y minus xy squared plus 4x, then the first order partial derivative of z with respect to x will be 12x squared y minus y squared plus 4. And differentiating z partially with respect to y, we get 4x squared minus 2xy. So these are the two first order partial derivatives. So the next thing we are going to do is equate these two partial derivatives to 0. So we form two equations in two unknowns, x and y. So the problem is now to solve these two equations. Here, we may start with the first equation, the second equation here, equation 3.6, which we can write as 2x into 2x squared minus y is equals to 0. So once we write this, then we can say either 2x is equals to 0, from which x is 0, or 2x squared minus y is equals to 0, from which y is equals to 2x squared. So from this equation, we get either x is 0 or y is equals to 2x squared. We can now substitute these values into the first equation, equation 3.5. If you substitute x is equals to 0 into equation 3.5 here, the first term becomes 0. So you get minus y squared plus 4 is equals to 0, or y squared is equals to 4. So from here we can get y squared is 4. So we take the square root on both sides, and that will give us y is plus or minus 2. So that we see that when x is 0, y takes the values plus or minus 2. So we either have the point x is 0, y is 2, or the point x is 0 and y is minus 2. So this gives us 2 points. If on the other hand we substitute y is equals to 2x squared into equation 3.5, see the equation 3.5 is here. We substitute y is equals to 2x squared. This should give us this equation, which can be simplified into this, so that we get x raised to power 4 is equals to minus 1 over 5. This one has no real solutions. So we cannot, this is 1 over 5. 1 over 5. We see that there is no real number that you can raise to power 4 and get a negative quantity. So this one has no real solution, meaning that this function has two stationary points. The stationary points occur when x is 0, y is 2, and when x is 0 and y is minus 2. Those are the two stationary points. Next thing is to determine the nature. Now we know the stationary points, but we don't know whether these are maximum, minimum, or saddle points. So the next thing we want to do is to determine the nature of these points. So to determine the nature of the points, we find what we call the discriminant. We shall denote this by the Greek letter delta. Delta is equals to the square of the mixed second order partial derivative minus the product of the other two second order partial derivatives. So what we do is that we evaluate this value at each of the stationary point that we obtain. If the value of delta is positive, then the stationary point is a saddle point. If on the other hand, the value of delta is negative, that is less than 0, then the point could be a maximum or minimum. And to determine whether it's a minimum or maximum, we find the value of the second order partial derivative. That is, we find d squared z by dx squared or d squared z by dy squared. We find any of this. We find any of this at the stationary point. If their value, they will have the same sign. They may not have the same value, but the sign will be the same. We will be interested in the sign. If the value is positive, then the point is a local minimum. But if it is negative, then the point is a local maximum. So let's go back to our function there and try to classify the points that we obtain, 0, 2, and 0, minus 2. We have the function whose stationary points we had obtained. Then we find the discriminant quantity. We have this first order partial derivative, meaning that we can differentiate this partially with respect to y to get the mixed order derivative. If we differentiate this with respect to y, then we'll get 12x squared minus 2y. Then if we differentiate with respect to x partially, we get 24xy. And if we differentiate the second function here partially with respect to y, we get minus 2x. So when we substitute these values here, you see delta now, we have 12x squared minus 2y squared minus 24xy times minus 2x. Now, we do not need to simplify this, but maybe this one we can write it as 12x squared minus 2y squared. Then plus the second term we can write as 48x squared y. We may not need to necessarily simplify this further. So what we need to do is to find the value of this quantity at each of the stationary points. Remember, our stationary points are 0, minus 2, and 0, 2. These are the two stationary points. So if we take the first one here, 0, minus 2, x is 0, and y is minus 2 at that point. So we are going to substitute x is 0. So we substitute 0, x is 0, and we say that so delta will be 12 times 0 is 0, minus 2 times minus 2, so that will give us plus 4 squared, then plus 0, and this will be equals to 4. This quantity is positive. This one is greater than 0. And we have said when delta is greater than 0, then the point is a saddle point. So 0 minus 2, in this case, is a saddle point. Then we can go to the next point. The point is 0, 2. Here, x is 0 again, and y is 2. If we substitute again, we get 12 times 0 minus 2 times 2. Then the second time again is 0. So when we square, this is minus 4. But when we square, we get delta is equals to 16, which is positive again. This one was also 16, not 4. This one was also 16 because it is 4 squared. So this one again, delta is 16, which is positive. And so again, the point 0, 2 is a saddle point. So this function has two saddle points. It has no local maxima, neither does it have a local minima, but it has two saddle points. Let's do another example. You are required to find and classify the stationary point of the function z is equals to x cubed plus 6xy minus y cubed. So the first thing, as we've said, is to find the first order partial derivatives, as we have here. Then remember that the stationary point is the point where the rate of change is 0. So we equate these two equations to 0 and solve the resulting equation. So once we equate to 0, we have this. Then from the second equation here, 6x minus 3y squared is equals to 0. We can write 6x is equals to 3y squared, from which when we divide both sides by 6, we can get x is equals to a half y squared. Then we substitute this into the first equation. X is equals to a half of y squared. So we're going to substitute this here, where we have x. So in this case, we get 3 into y squared over 2 squared minus 6y. And this will give us 3 all over 4, y raised to power 4 minus 6y is equals to 0. 3 over 4 y squared minus 6y. Sorry, the sign was positive. This is plus, not minus. From here, the sign was positive, plus 6y. So we can multiply both sides by 4 to get 3y raised to power 4 plus 24y is equals to 0. Then we can factor out 3y. Then we get y cubed plus 8 is equals to 0. So that either 3y is 0, from which y is equals to 0, or y cubed plus 8 is equals to 0. If you solve the second equation here, we get y cubed is equals to minus 8, and y is the cube root of minus 8, which is minus 2. So we have two possible values of y. Either y is 0 or y is minus 2. So once we have that, we can go back to the relationship between x and y. So we can say when x is 0, when y is 0, when y is equals to 0, we get x is equals to 0. And when y is minus 2, we get x is equals to minus 2 squared divided by 2, which is 2. So that there are two stationary points. X is 0, y is 0. And the second point is x is 2 and y is minus 2. So those are the two stationary points. The next thing is to determine the nature of each of these points. The next thing is to determine the nature of each of the stationary points. So we find the discriminant here, delta. So this means that we need first to find the second order partial derivative. Since we have the first order partial derivatives here, we can differentiate this partially with respect to x to get this. If you differentiate the first equation here partially with respect to x, we get 6x. And if you differentiate the same partially with respect to y, then we'll get 6. Then when you differentiate the second one partially with respect to y, we get minus 6y. So these are the second order partial derivatives. Then we substitute here. So we see that the delta will be 6 squared minus 6x times minus 6y. So this is 36 plus 36xy. So we now find the value of delta at each of the stationary points. So at the first point, which is 0, 0, x is 0, y is 0, we can substitute here 36 plus 36 times 0. That will give us 36, which is positive. That means that the point 0, 0 is a saddle point. If we go to the next point, 2 minus 2, x is 2, y is minus 2, then you see that delta will be 36 minus 36 into 2 times minus 2. Sorry, this is plus. And if you work out this will be 36 minus 144, which will give us negative 108. This one is negative. It's less than 0. So we need to find the value of d squared z by dx squared at that point. Remember, this quantity was 6x, but we want to find its value when x is equals to 2. That's the value of x at the stationary point. So this will be 6 times 2, which is 12. 12 is greater than 0, meaning that the point is a local minima. The point is a local minima. So basically, this is how we find the stationary points for functions of two variables. Now, we have another example here. Of course, I'll share these notes so that you can work out. You find and classify the stationary points of this function. We have the partial derivative of z with respect to x and the partial derivative of z with respect to y. So we find those. Next thing, we equate each of the derivatives to 0. So we have these two equations, and from the second equation, we get 2xy is equals to 0, which means that either x is 0 or y is 0. So either x is 0 or y is 0 from this equation. We substitute each of this into the first equation. If we substitute y is 0 into this, then we get 3x squared minus 3 is 0, from which 3x squared is equals to 3. and x squared is 1 when we divide both sides by 3, so that x becomes the square root of 1, which is plus or minus 1. So in this case, you see that when y is equals to 0, x takes the values of plus or minus 1, and this will give us the point 1, 0, and minus 1, 0. So when y is 0, there are two stationary points. And then we consider now the case when x is 0. If you go back to this equation and substitute x is 0 here, then you get minus 3 plus y squared is equals to 0, which is this one. And from this equation, you can get y squared is 3, and y is equals to the square root of 3, which is plus or minus. There are two values, plus or minus. So that that means that when x is 0, y takes either positive root 3 or negative root 3. So that in this case, we get some other two stationary points, 0, root 3, and 0, negative root 3. So in total, this function has 4 stationary points. This function has 4 stationary points. To determine the nature, then we need to find the second order partial derivatives. We compute delta. Delta will give us this. And then we find the value of this delta at each of the stationary points. So we have 1, 0 is a local minima. Sorry, there is an error here. 1, 0 is a local minima. Then minus 1, 0. This should be minus 1, 0. Minus 1, 0. That one is a local maxima. Then we have a saddle point at 0, root 3, and another saddle point at 0, minus root 3. So that this function has two saddle points, a local maxima and a local minima. So basically, this is how you find the stationary points. So I'll share this note so that you can go through them again. And then you can work out the last two. So I think for this session, we'll edit that. And this is our last part in this topic, the stationary points. Thank you for watching.